Welcome back. That was Bach's Air on the G string. We're going to talk about that again at the end of the lecture, and I hope that this lecture helps you understand it a little bit better. In the first lecture, we played a note on any instrument. We played many of them, and we found that a note on any instrument includes many different frequencies. As we learned, those are frequencies and not pitches. Pitches is the musical term for how high and low a note is. These are called overtones or harmonics. For many instruments, these overtones are related to the harmonic sequence. In wavelengths, that's 1, 1/2, 1/3, 1/4, 1/5, 1/6. And if we look at frequencies instead, those are the ratios 1 to 2 to 3 to 4 to 5, 6, on and on up. Now we make different pitches on instruments by changing the vibrations in mathematically predictable ways, whether it's shortening the string on a violin or putting holes in a flute to shorten the length of a vibrating tube of air. On the Bach Air that we opened with, all of those notes are on the G string. That's what it means, Bach on the Air on the G string, and it's all on my lowest string right here. We're shortening the G string to get different notes. Why did they decide to put it on the G string? That's today's topic, and that's timbre. I want to start by giving an informal definition of timbre. Timbre is the quality of sound that allows one to distinguish between two notes of the same pitch and the same loudness. If you play a flute and a violin, they could play the same note and the same loudness, but you would still know the difference between a flute and a violin. Why do you know that difference? Timbre. Here's a more formal definition. If you want to know a formal definition for any musical term, you turn to the Grove Dictionary of Music. And if you look up in the Grove Dictionary, it says this: timbre is, and I quote, a term describing the tonal quality of a sound. A clarinet and an oboe sounding the same note at the same loudness are said to produce different timbres. Timbre is a more complex attribute than pitch or loudness, which can each be represented by a one-dimensional scale, high-low for pitch or loud-soft for loudness. I have to interrupt at this point to say we're actually going to find out that the high-low for pitch isn't as easy as it might sound, and we're going to hear that in Lecture 3 in Auditory Illusions. The end of the Grove Dictionary of Music definition includes the following line. Timbre is defined as the frequency spectrum of a sound. Spectrum. That's where the math comes in. That's what we saw last time. We saw graphs showing how much of each vibration you heard, how much of each overtone. That's the mathematical connection to timbre. I also want to give you what's a negative definition of timbre. It comes from the American National Standards Institute, ANSI. They define timbre as everything that is not loudness, pitch, or spatial perception. And that's a different one, spatial perception. Neither of the other definitions mentioned that. Spatial perception is that you can tell where a sound is coming from. If I hear a sound on my left side, how do I know it's on my left side? Interestingly, your brain does this amazing calculation. That sound reaches my left ear first. It comes over and reaches my right ear a little bit later. The reason I know that it's not two sounds is that my brain decides that's not two different sounds, one before the other. Instead, my brain realizes that it's one sound, and because it hit my left ear first, it must be coming from the left. Now, today's topic, timbre, interestingly, also has a brain aspect to this. There's a combination of brain and your ear that combine to tell a flute from a violin. The surprise here is that your ear and not your brain does the complicated math. The mathematics we're going to talk about today, and the mathematics we need to understand to get through the mathematics of timbre, is the Fourier transform. What the Fourier transform does is it breaks a complicated wave into simpler sine and cosine waves. Amazingly, and somewhat unexpectedly, the reason we care about this is that the human ear does a Fourier transform. It does that sort of complicated mathematics. You hear the difference between a violin and a flute because your ear is doing this complicated math and sending the results of that complicated math to your brain. Once we understand timbre and how to change it on a violin, then we can actually use at the very end, I'll show you how violinists use fractions in order to show off. Let's listen to some examples. The definition suggests that we can distinguish among different instruments playing at the same pitch and the same loudness. So let's try. Here are 4 A's in a row. And ask yourself, what instrument is each one of those? Here's the first. Here's the second. Here's the third. And here's the fourth. In order, those were a trumpet, a violin, a clarinet, and a pure sine wave. That last one wasn't actually an instrument at all. Let's use mathematics to help us understand timbre. We can look at the waveform, and let's look at the sine wave first. The sine wave is the pressure variations. The horizontal axis here is time, and the scale here is that from one peak to the next is 1 over 440 seconds. This is a sine wave which is at 440 hertz. So the sine wave is going back and forth 440 times per second. So one complete cycle of that takes 1 over 440 seconds. Now the vertical axis here is pressure. The 0 in the middle is atmospheric or ambient pressure, and when you have a peak, that's where you have higher pressure, where the air molecules have compressed and are at higher pressure. And where you have a trough, that's below ambient pressure, and that's where the air molecules are more spread apart. That's called rarefaction. If we look at a violin waveform, we can hear this on an A. We can hear it on the A of a violin. So here's an A on a violin. And here's the waveform that goes with it. And you can see it's much more complicated than just a sine wave, but it is also periodic. How frequently does it repeat? Well, if you look from one peak to the next, it's exactly 1 over 440 seconds. And that's because this A was a 440 hertz A. So how do we look at the spectrum? Remember, the Grove definition was the frequency spectrum of a sound. What is the spectrum? The spectrum is the answer to the following question. How would you make this wave by adding up pure sine waves of different frequencies? In other words, the spectrum is tells you what the recipe is to cook up a particular sound, a particular wave, using sine waves as the ingredients. Now you remember, sine waves you probably remember from a high school trigonometry course. These are the simple building blocks of trigonometry. If you had a right triangle, it would be the length of the opposite side over the hypotenuse. If you were working on the unit circle, you'd be looking at the y-coordinate on the unit circle. When we graph a sine wave, it looks like this. It's sort of simple, regular, going back and forth. Now we can stretch and squeeze a sine wave. We could, instead of just taking sine of x, we could take a times the sine of bx, or even a times the sine of bx plus c. Those are all variations of a sine wave. The a increases the amplitude, the b squishes and shrinks it this way, and the c shifts it over left and right. What does it mean to add up these waves? We said we're looking at the recipe, how to sort of cook up a sound. And to do that, we combine these ingredients with addition mathematically. And it turns out that sound waves add just like functions. Let's hear a 440A, again a sine wave. And here's a 500 hertz sine wave. Now we're going to add them together. Here, let's listen to it first. Here's a 440 hertz sine wave plus a 500 hertz sine wave. And mathematically, we're simply adding those together. At every point in time, we're going to take the pressure value we get from the 440 hertz and the pressure value from the 500 hertz. We're going to add those together. And so if they're both high, if they're both in their peak portion, then we're going to add and get something even bigger. If one is in a peak and one is in a valley, then they're going to cancel each other out and get something near zero. Now that's an example of taking two ingredients, the 440 hertz A and the 500 hertz A, and putting them together to get a particular dish, the sum. Let's see if we can go in reverse. Take the dish and then figure out what is the recipe that gave us that. So here's a particularly interesting dish. This is a sawtooth wave. Let's hear the sawtooth wave. Notice that the timbre is very different from the other A's you heard. It sort of has an edge to it. So the question we're asking is, which sine waves would you add up to get that? Now we have some clues here. We played a 440 hertz sawtooth wave. And that means we would need to add up sines that have the same period, that fit nicely within the same period that the sawtooth wave is vibrating. In other words, we need sine functions that repeat every 1 over 440 seconds. That gives us some idea of which sine waves we should take. In fact, if f is the frequency, we should take sine functions that have 2k pi over f times t as their argument. For k equals 1, 2, 3, on and on up. All of those have the correct period. And so we have an idea what the ingredients should be. We might try to add up and get a sawtooth wave, s of x, by taking sine of 2 pi over ft, plus sine of 4 pi over ft, plus sine of 6 pi over ft. And we might think about taking different amounts of those, and those are the AKs. And so now we've reduced it to a different question. How much of each one of those ingredients should we take? What should the AKs be? Now this is a quick math aside for those of you who know calc, because the way you figure out the AKs is this really wonderful mathematical trick called orthogonality. It turns out that if you take the sine of 2j pi t times the sine of 2k pi t and integrate from 0 to 1, you usually get 0. In fact, you always get 0 unless j and k are the same number. Mathematicians say that those two functions, the sine of j pi t and sine of k pi t, are orthogonal. It's a version of perpendicular. We can actually think of those functions as being vectors in some abstract function space, and those two particular vectors are perpendicular. On the other hand, if j is equal to k, then those two vectors are perfectly parallel. They're the same vector. And that allows us to do some interesting mathematics. If you're interested in this, look up orthogonality in Fourier series online. There's wonderful work on that. So this is all the work of Joseph Fourier. Who was he? Turns out that he was a mathematician born in 1768. He was one of at least 19 kids. We're not exactly sure how many kids there were. He was orphaned at age 8. He was very active in the French Revolution, and he was not only an expert in mathematics, he was also an expert in Egyptology. Interestingly, it was Fourier who first discovered the greenhouse effect, this effect of gases on the Earth's atmosphere keeping heat in. He didn't, of course, know about climate change at that point. Now, the story is that in 1830 he actually died in the somewhat ironic way. Sort of like the greenhouse effect, he would wrap himself in blankets instead of turning on the heat. And he quite possibly fell down the stairs when he tripped on one of the blankets and died in 1830. So Fourier was studying various problems when he came up with these Fourier series. The idea is that given any periodic function, he was looking for a recipe to write it as the sum of sines and cosines. That was what he was doing. He was doing this in the context of studying things like heat flow in metal plates. And his work, Fourier series and later Fourier transforms, is used to solve a wide variety of problems in differential equations. Anything from signal processing uses Fourier series and Fourier transforms. Mathematically, we call things the heat equation or the wave equation because they model heat transfer, or wave equations when they model what happens to waves as they move. Quantum mechanics uses Fourier series and Fourier transforms to study the topics that they're looking at. Most problems involving periodic functions use Fourier series or Fourier transforms in order to figure them out. So let's go back to the problem we were working on. We were looking at a sawtooth wave, and here let's listen to it again. And we had figured out that the ingredients for the sawtooth wave were probably these sine functions. But interestingly, unlike regular recipes in the kitchen, this recipe looks like it goes on forever. It's an infinite series. And now we're trying to answer the question, how much of each one of the ingredients should we take? That's where we turn to this orthogonality trick. And the answer we get from this orthogonality trick is that we should take them in the following amounts. The first sine wave we should take with amount 1, and the next one 1/2, and the next one 1/3, 1/4. We've seen that before. That's actually a copy of the harmonic series. Isn't that amazing? Mathematics is like that. The same things come up again and again and again. So now that we have an answer, let's be good math students and check to see if that works. And interestingly, we can check both graphically and with sound. As we add more terms, as we add more of these ingredients at the correct proportions, does the function look more like the sawtooth wave? And does it sound more like the sawtooth wave? The key idea here is approximation. We're going to approximate the sawtooth wave by taking more and more terms in the series, by taking more and more ingredients in our recipe. So let's look at this. Here's just the first sine wave, and when we add another term, we get something that looks closer. And when we add another term, we're getting even closer. Every time we add another piece of our recipe, we're getting closer and closer to our sawtooth wave. By the time we added a lot of them, we're actually getting very close to the sawtooth wave. That looks good. Graphically, it looks like we're getting closer to the sawtooth function as we add more and more ingredients in our recipe. Well, let's ask the related question, does the same thing happen with sound? If we add up more and more ingredients, if we put more ingredients in the pot, does it sound more and more like the sawtooth wave? Well, let's listen. When we put the first ingredient, that's just a sine wave. Let's listen to that. When we put the second ingredient in, we're only taking half of that, half of sine of 4 pi over f times t. And now we add those together, here's what we get. And with 3 ingredients, we get this. And 4 ingredients. 5 ingredients. Well, cut, here's the first 10 ingredients all added together. And just to compare, that's sounding more and more like the sawtooth wave. Here's the sawtooth wave that we're aiming for. Now let's look at related mathematical questions. You can already see that this is working. This recipe is giving us the function. But mathematicians ask a lot of different questions about this once they figured this out. And mathematicians since Fourier have answered many of these questions about approximations. So let's look at a function g and think of it as writing it as the sum of different sine waves. When we add up the sine waves, do we always get g? Do we get g everywhere? You'll notice in that sawtooth wave there was this jump when we got from the top of the sawtooth wave to the bottom. And if you look closely, the approximations actually overshoot that jump a little bit. What's going on with that particular point? How quickly will our recipe converge to the dish we're looking for? How quickly will the sum converge? And can you estimate the error? If you take only n terms, maybe 100 terms, how far off are you going to be from the eventual function that you're trying to approximate? If 2 functions have the same Fourier expansion, are they necessarily the same? Interestingly, this is what Georg Cantor was working on when he came up with his theories about different sizes of infinity. It was actually Fourier series that he was working on. Let's look at a couple of important generalizations of Fourier series and how we use them to understand musical sounds. So far, we've talked about what are called Fourier sine series. We're only using sines. Now, there are 2 important generalizations to this. The first is that we could use sines and cosines, but stay with these even multiples of pi for our frequencies. So pi, 2 pi, 3 pi. If we use sines and cosines with those as the argument, those are called Fourier series in general. The second generalization we could make is to allow any frequency, not just integer multiples of pi. And if we do that, we get the mathematics called a Fourier transform. In all of these cases, the point is to break down a complicated periodic function into simple sine waves that we understand much better. Now, I don't want to get into the details of this, but I do want to tell you a little bit about the tools that you would need to understand in order to get into this mathematics. It's beyond the scope of our course here. The mathematics is incredibly advanced. It would take semesters to cover. But you need things like complex numbers. You need exponentials. You actually need something, a generalization of functions called generalized functions, the most famous of which is the delta function. You may have heard about that if you've taken a physics class. The idea, again, is that you have your waveform on the time side, the pressure wave in terms of music, and you also have the spectrum, the frequency side. And it's this wave side versus the frequency side that becomes really important. The spectrum shows us what frequencies of sines and cosines make up the waveform. This mathematics is key to virtually all signal analysis, including AM-FM transmission. AM is on the wave side and FM is on the Fourier transform side. And sound compression, which we'll talk about in lecture 11. The key mathematics in quantum mechanics is actually exactly this. It's Fourier transforms. You may have heard of the uncertainty principle. The key behind the uncertainty principle is a particular Fourier transform. So that's a lot of complicated mathematics. What do you need in order to follow this particular lecture? Well, you need to know that the Fourier transform takes a complicated wave and breaks it down into component sine waves of different frequencies, and that we call that the spectrum. It's important to know also that this is reversible. You can go from the waveform to the spectrum and back. You're going from the waveform, the function, to the frequency and back. And mathematicians call that going from the function side to the Fourier transform side, and then doing the inverse Fourier transform to get back. And you also need to know that that's what our ears do. Our ears are doing a Fourier transform. The rest of this lecture is going to be using these tools to understand instrument sounds, starting with an A. So let's return to this simple sine wave A at 440 hertz. So here it is visually. That's a sine wave, and again, peak to peak, we're looking at a gap of 1 over 440 seconds. The spectrum of this, if we take the Fourier transform, is showing a single peak right at 440 hertz. Now in theory, it's a single infinitely tall point. It's a delta function. In practice, the computational issues smooth this out, and so you see sort of a peak sort of smoothing out to the sides. Does this sort of pure sine wave ever occur? Does anything vibrate in just a sine wave? It turns out that some bird calls are very close. Here's the call of a black-capped chickadee. If we look at its waveform, that looks remarkably like just a simple sine wave. It didn't have the complications that a violin or a trumpet had. Its spectrum is nearly a single peak, right at 3,850 hertz. All of the other overtones are much, much smaller. Now, it's important to note that the vertical scale here is logarithmic. Each one of these lines is 10 decibels. And 10 decibels doesn't mean you subtract 10 from something, it's multiplicative. And so when something is 3 lines below, 30 decibels below, that's actually 10 times 10 times 10 less. It's 1/1000th as powerful. So this chickadee is singing almost a pure sine wave, and all of the other frequencies are very much softer. Let's go back to the sawtooth wave and look at its spectrum. The sawtooth wave looks like this, and we've already figured out the recipe for the sawtooth wave. And when we look at its spectrum, it shows us visually the recipe we use to get us. It shows us that each one of these frequencies we take in a smaller and smaller proportion. That's the harmonic series that we saw in our recipe. 1, 1/2, 1/3, 1/4, on and on. And so this is confirming our idea of the correct recipe for the sawtooth wave being exactly what we figured it out to be. Let's look at some spectra of musical instruments. Here again is an A on my violin, 440 hertz. And when you look at the spectrum, well, let's look at the waveform first. You can see that it repeats, and those gaps are again 1/440 seconds. But if you look at the spectrum, we saw in lecture 1 that it had peaks at multiples of 440. Today, we're really concentrating on the heights of those peaks. How much of each harmonic are we hearing? Now, when you look at the spectrum, you look at the second harmonic, the one that's at 880 hertz, is actually 20 decibels below the first one, the fundamental. That means it's 100 times lower. On the other hand, the fifth harmonic is almost as loud as the fundamental. That's very characteristic of a violin. Let's look at the spectrum of a trumpet. Again, when we look at the waveform of a trumpet, we see that it's periodic, that it repeats every 1/440 seconds. When we look at the spectrum, what we see is that we see peaks at the multiples of 440, but the heights of those peaks form a very different pattern from what we had when we were looking at the violin. Let's look at a clarinet. A clarinet waveform looks like this, and again, the peak-to-peak distance is 1/440 seconds because it's an A, 440 hertz. But the spectrum has something interesting about it. If you notice, all of the odd overtones of the clarinet sound are much louder than the even ones. The fundamental is very loud, the second one is small. The third harmonic is loud, the next one is small. And in every case, the even ones are much smaller. That has to do with the closed-endedness of the tube in a clarinet. So now let's compare all three of these instruments together. Here we have a violin spectrum, a trumpet spectrum, and a clarinet spectrum. These different instruments have different patterns. And let's go back to the question we had. Why should we care about the spectrum of the Fourier transform? The answer is that our ears do exactly this. It's how we distinguish different instruments and different voices from different timbres, and it has to do with the heights of these various peaks. How our ears do it is fascinating and has a mathematical component to it. So let's look at that. Our ears use something called resonance. Now this isn't just musical instruments that give you resonance. Violin strings, twirling tubes, singing in the shower, these are all versions of resonance. Sometimes you get beautiful and sometimes even catastrophic things when you have resonance. Bridges sometimes collapse because of resonance. Resonance is most commonly cited as the cause of the Tacoma Narrows bridge collapse. They call it galloping Gertie, and you can see really shocking videos on YouTube of this bridge collapsing. And that's maybe because of resonance. When you drive down a dirt road, we had a lot of dirt roads back in Wisconsin, and when you drive down a dirt road, sometimes you hit what's called a washboard section where it's bump, 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 regularly spaced bumps. Interestingly, If you hit that at exactly the right speed, it's horrible. Your car starts to shake and rock and roll. And it's because you've hit it when the shocks have their resonant frequency. If you speed up or slow down, either way, you'll get away from the resonant frequency of your shocks and you won't have that horrible reaction. Now, it's a little bit ironic because the washboard is caused by previous cars going over that and by their shocks going at a particular rate. And so that's how you get washboard, and it's also how you avoid it. You go at a different speed than everybody else was traveling. You see resonance when you see a wine glass breaking. If you want to break a wine glass, first you clink the glass to find its resonant frequency, and then you sing or play a very loud noise exactly that frequency. What it's doing is it's forcing the glass to vibrate in its resonant frequency, where it vibrates a whole lot, and then finally breaks. Now the underlying mathematics here has to do with differential equations. And the models that we talked about last time, if you apply those models in all of these cases, you get phenomena that have key vibrational modes, and those are called the resonant frequencies. If you force that system at exactly that frequency, the solutions become very large. There's a very dramatic example of this up in Canada. The Bay of Fundy has tides that are over 50 feet from top to bottom. When the tide goes out, the water goes down 50 feet. The reason has to do with resonance. The Bay of Fundy has a particular resonant frequency, and in fact, it's the same as the tidal frequency. Interestingly, you can think of the Bay of Fundy as more of a clarinet because it's closed at the other end. It's not like a flute open at both ends. Also, if you think about it, if the Earth turned a little faster or slower, then the length of the Bay of Fundy would have a resonant frequency that's different from the tides. And you wouldn't have these wildly changing tides in the Bay of Fundy. But maybe there's some other bay on Earth where you would all of a sudden hit its resonant frequency. The key here is that different sized objects have different resonant frequencies. And if you hit the resonant frequency, it sounds very loud. So what does this have to do with your ear? Let's take a trip inside your ear and see how it works. Deep inside your ear, on the other side of the eardrum, is a little organ called the cochlea. It's sort of conical shaped. It actually looks to me a little bit like a French horn. And what happens inside your cochlea is different sizes at different places. And what that means is that different places resonate at different frequencies. If a particular sound comes in, if a particular sine wave comes in, there's some place in your cochlea where that resonates very loudly. And the basilar membrane is inside the cochlea, and it picks up those vibrations, exactly where in your cochlea it's vibrating, and sends that message to your brain. What it's doing is your ear is figuring out a recipe for that sound. Let's walk through what happens when you hear a violin playing a note. When I play an A, the sound wave hits your ear, and the vibrations hit your ear in terms of a wave front, like this. And so that's the pressure changes that we've seen before. But each overtone in the spectrum, each element in our recipe, each ingredient resonates the cochlea in a different place and with a different amplitude. It's a different force on your basilar membrane. What your ear is doing is exactly what the Fourier transform is doing. It's separating a complicated wave into simple sine functions and sending those to your brain. It's sending the signal, it's sending the recipe back to your brain. Let's look at some other instruments. What your brain is doing to tell the difference between, say, a violin and a clarinet, we've seen both of those spectra now. What your brain is doing is your brain has stored up patterns of spectra from various instruments. And your brain knows that a spectrum of a particular pattern is a violin, and a spectrum of this different pattern is a clarinet. And what your brain is doing is pattern matching and telling yourself, oh, I've seen that pattern before, I've heard that spectrum before, that's a violin. Now I want to be careful. It's a little bit more complicated than I've told you so far. And there's a caveat to all of this. The spectrum changes over time, and it turns out that the spectrum of the very beginning of the note, what musically we call the attack, is incredibly key. To illustrate this, we've used a little bit of trickery electronically. What we've done is we've recorded a note on an instrument, and now we've electronically taken off the attack. Gordy has taken the very initial part of the sound off of this. So let's hear it. Here's a note on an instrument, and I want you to guess, what instrument is that we're hearing? When I've played this for my students, they think it sounds a little bit like a piano, like something like that, like some vibrating string like that. Well, here it is when we actually put the attack back. Here's the full note. You can hear it's actually a banjo. The pluck on the banjo gives the initial part of the spectrum lots of high overtones, but it turns out that those high overtones die out very quickly. And after that period, you're left with just a vibrating string, just like a vibrating string on a violin or a piano. The piano has a very soft attack, and that's why when we take the attack off of the banjo, it sounds a lot like a piano. The timbre here is important, and the timbre of the attack is particularly important. We can also look at the different timbres that you can create on a single instrument. So let's go back to my violin. Here are 4 different ways to play a 440 Hz A on a violin. These are essentially 4 different recipes using the same ingredients, the same sine waves, just different amounts. And we'll play them for you from recording first of all. Can you tell how I'm playing my A's in these 4? Here's the first. Here's the second. Here's a third way of playing an A. And here's a fourth. I'll play those so that you can see them. The first one was a pizzicato, like this. The second was just an open A, an A with no fingers on it, like this. The third one was the same note, but on my G string, all the way up here. And the last one was something called playing ponticello, playing with my bow very near the bridge, like this. Let's look at the spectra of those 4 sounds. And we're not going to look at the attack. We're going to look at after the attack, the spectrum of the continuous part, the ringing part of those sounds. Let's look first at the pizzicato. Here's the pizzicato again. And here's the spectrum of the open A, and we can listen to it. Here's the spectrum of an A played on my G string. And finally, here's the spectrum of a note played ponticello near the bridge. What do we see in there? There are differences in these spectrums. So let's look at these more closely. The pizzicato is all about the lowest overtones. The attack would have the higher overtones, but they've died out fairly quickly. And the spectrum is now showing us not the attack, but the ringing part, which is only the lowest overtones that have come through. The open A has a rich set of overtones in most ranges. You can see all the way through these ranges up to the higher frequencies. You see a lot of all of these. The A on the G string, the higher overtones are much quieter. The recipe calls for much less of those higher overtones and just more of the initial ones, the lower frequencies. And when you play ponticello, I want you to look closely here, from about 3,000 Hertz to 5,000 Hertz. They're even louder than the open A. That's what's giving the ponticello note the sort of pinched, icy, edgy sound to it. There's another way you can change the timbre of an instrument, and that's called harmonics. Now I know it's a bad word. We've already used the harmonic once, that word once. String harmonics that I'm about to play for you are different from the harmonics that describe the modes of vibrations, the overtones. They're related, but they're not the same. The idea here is that we lightly stop the string from vibrating at a particular point. If I press hard on the string, what I'm doing is I'm shortening the effective length of the string. Only this part is vibrating. What I'm asking to do now is just press lightly on the string to stop it from vibrating. If you think back to the jump rope demonstration, you can imagine when we have the jump rope going, you can imagine somebody coming in and stopping the string in the middle. So let's ask ourselves, what would happen? that fundamental frequency, the fundamental mode where the whole string is vibrating, if somebody stops the string in the middle, that's going to be completely disrupted. The string is trying to move in the middle. Contrast that with the second harmonic, the first overtone, where we have one loop here and one loop here. There's actually a node right in the middle of the jump rope. And if somebody were to stop the string right in the middle, there's no problem with that. The string can continue to vibrate on each side, even when somebody has their finger lightly touched in the middle. The third mode, well, there's a small loop right in the third mode, but the fourth mode had 3 nodes, and one of the nodes was right in the middle of the string. And so if somebody were to put their finger and stop the string right there, there would be no problem with that. When you think through all of this, what you come up with, what you realize, is that all of the even modes would have nodes in the middle, and those would be allowed, and all of the odd modes wouldn't, because they are moving in the middle. We can hear what this sounds like, because I can do this on my violin. Here's the original A. And here's the A we get when I slightly touch the string right in the middle. And when we look at the spectrum of those two, you see it acts exactly like we just described mathematically. The harmonic is giving you only the even overtones. All of the odd ones are damped out. The person touching the string there is not allowing the string to vibrate at the odd modes, just the even ones. I also want you to notice that we just changed the fundamental. The lowest frequency is no longer 440 hertz. The lowest frequency is actually what musicians call up an octave. We'll talk more about intervals later. The lowest frequency is now 880 hertz. It's double the fundamental frequency of the original. Now there's nothing special about 1/2. We could stop the string in lots of different places. If we stop the string 2/3 of the way up, what happens? When we think through the example of the jump rope, 2/3 of the way, we would only hear the modes where there's a node at that place. The fundamental doesn't have a node there. The second harmonic doesn't have a node. It's the third one that vibrates in 3 pieces. That had a node 2/3 of the way up. And in fact, when you think through it, only the multiples of 3 will have nodes at 2/3. We should hear only every third overtone. Let's see if that actually happens. Here again is the full A. And here's a harmonic when I stop the string 2/3 of the way up. And you can see in the spectrum that all of them but the multiples of 3 are gone. The timbre and the fundamental have changed. The timbre has changed because we've eliminated some of the overtones. The fundamental has changed because the lowest frequency we hear now is 3 times the original fundamental's frequency. It's the third harmonic, the second overtone, and it's what musicians would call an E. That was 2/3, but what about 1/3? This was 2/3, 1/3 is somewhere up here. And if you think about the analysis with the jump rope, the mathematics should be exactly the same. Stopping the string 2/3 of the way up the string and 1/3 of the way up the string should give you identical mathematics. Again, only the multiples of 3 should work. Let's test this. Here again is stopping the string 2/3 of the way up the string. And let's test this and see what happens if I find 1/3 of the way up the string. Let's see what that sounds like. Again, 2/3, 1/3. Those sound almost exactly the same. And if you look at the spectra, you'll see that they are very similar as well. They have the peaks in exactly the same places. That's because we're looking at only the multiples of 3 in the original overtone series of the A. And they have very similar heights of all of the overtones. They have very similar timbres. And this is how violinists use fractions to show off. If you're asked to play a note that's exactly this note, you have 2 options. You could either play the note by hitting it and stopping the string at 2/3 of the way up like this, or you could play the same note with the same timbre by finding the point way up here and playing it up there. Now, violinists are sort of notorious in the musical world for being cocky and being show-offs, and violinists know that it looks much more impressive to stop the string up here to find this place than it does here. And so every violinist is going to try to hit this one just because it looks better. You're asked to play this exact note in the Mendelssohn Violin Concerto in the 3rd movement. I'm going to play it for you the easy way first, and I'm going to find this note right here. That was the easy way. The hard way is going to be to find the note way up here at 1/3 instead of 2/3. Here's the Mendelssohn Violin Concerto the way you'll always see it done in concert. Every violinist who's playing this will hit the harmonic that's way up here. That's how you'll see it done in concert. I want to talk about one other way to change timbre, and instead of the violin, I want to talk about it on the piano. If you're designing a piano, you actually have a choice, and the choice you have is where on the string should the hammer come up and hit the string. Different choices will actually give you a different timbres. Remember that when we were looking at the overtones, we were looking at the seventh of those. The seventh harmonic was not a note that was on our 12-tone scale. So when we're making a piano, we can choose to put the hammer in a place so that the seventh overtone is less heard. To avoid the seventh one, we make this following decision about the hammer. To avoid the seventh harmonic, the one that's not on our scale, we position the hammer exactly 1/7 of the way up the string. To understand this, think back to the jump rope. The seventh harmonic is going to have 7 loops. It's going to have a node 1/7 of the way up the string. If we hit it there, we're going to disrupt that mode, and so you're not going to hear any of the seventh harmonic. String harmonics, we're trying to keep the string from vibrating at particular points, and we're stopping the string at those particular points. We're eliminating those modes. Here, we're forcing the string to vibrate in a particular place, and we're therefore eliminating any of the overtones that have a node there. Pianos are actually made this way, and when I talk to pianists about it, they're always a little bit surprised. I sometimes can almost see them running back to their offices to measure the strings. And it turns out not all of the hammers are at 1/7. Sometimes it's a little bit too close, there's not enough room, and when they can't fit a hammer at 1/7, they put it at 2/7. But the mathematics is the same, it eliminates the seventh harmonic. So that finishes our discussion on the mathematics of timbre and individual instruments. And let's talk a little bit about how individual composers use timbre in composing music. The primary way that composers use timbre is by choosing different instruments for different parts. Think about a piece like Peter and the Wolf by Prokofiev. The bassoon represents the grandfather, and the oboe with its very different timbre, sort of a pinched sound, represents the duck. And the flute, the flighty flute, represents the bird. The percussion is actually the hunter. These are different timbres for different instruments because of the storyline. A more subtle way of doing this is not asking different instruments to play different things because of the difference in timbre, but asking a single instrument to play in different ways, plucking, bowing, or playing harmonics. And that takes us back to the opening music, the air on the G string. Bach wrote the Orchestral Suite No. 3 around 1731, but it was August Wilhelm, a German violinist, who adapted it just for violin and piano. He changed the key to C, he brought it down a little bit, and he also decided to have a violinist play it entirely on the G string. Now violinists can tell which string you're playing a note on by the timbre. And so this is how we get the air on the G string. Interestingly, this was the first piece of Bach ever recorded back in 1902. We're going to close with the second half of the piece we started with. This is the second half of the air on the G string. And this is what I want you to think about while we're listening to this. I want you to think about the choice of instrument that was made by Bach and Wilhelm. The choice of instrument by Bach was to play it on a stringed instrument. The choice by Wilhelm was to bring it down an octave and then to not play it like I just played, but play it only on the G string. It gives it a darker quality. How do you perceive this? You perceive this because your ear hears this. It hears the darker quality via a Fourier transform. That's what your ear is doing, breaking down a complicated wave into its constituent pieces, figuring out what the recipe for that particular sound is. That tells us the overtone series that we saw in lecture 1, but the amount of each one of those tells us the timbre. So listen as your ear does a Fourier transform. Listen to the air on the G string, which emphasizes the lower, darker parts of this piece. Thanks for joining us. Next time, we're going to talk about auditory illusions. In particular, we're going to go back and see why pitch, high and low, is more complicated than you first might think.